Let's look at a chi-squared goodness of fit test for a one-way table. So this is a test for one population and one categorical variable. Let's take a look at kind of what all of that means. So here I have the categorical variable crime type, and there are 4 categories there, and then listed next to each category is its frequency, or how often it occurs. So together, this makes up a one-way table. Now, our null hypothesis for this test is that the population distribution closely resembles what's listed here. And our alternative hypothesis would be that it is not close to what is listed there. We have 3 assumptions and conditions to check in order to use this process. So the first is that we have a random sample of some sort. Okay, and here they pulled a random sample of 500 violent crimes, and they counted up how many were in each category here and then listed them. Okay, we will call these our observed values. So that would be our first assumption, is that we have a random sample that we're working with. The other 2 here, though, have to do with what's called an expected value. So we have our observed values, but to get our expected value, we're going to use this formula here. E is equal to NP. So our N is the sample size for our observed data. So our N here is 500, our sample size. And what we would do is, to get the expected value for each category, is we're going to multiply this proportion times our sample size. So this is our N times P, and we'll do that for each of these. Okay, once we've done that, there's 2 things we have to check in this list of what are going to be our expected values. So the 2 things we need to check is that none of these are less than 1. Okay, so they all need to be 1 or bigger. And then at most, 20% of them are less than 5. Or another way of putting this is that at least 80% of these expected values have to be 5 or bigger. If you've met all 3 of those, then what you're going to do is called a chi-squared goodness of fit test. Okay, so in order to calculate the test statistic for this test, what you're going to do is, for each category, you'll take the observed value and subtract the expected value and square it, and then divide by the expected value for that category. So you'll do that for the first category, the second category, the third category, through all the categories, and then you add all of those up. And that will be your chi-squared test statistic. And then to get the p-value associated with that, there are at least 2 ways to do that in Excel. The first is that you can just use the distribution command. So chi-squared.dis.rt, you would put in your test statistic and your degrees of freedom. Okay, and you can get your degrees of freedom. Your degrees of freedom are your number of categories minus 1. Or if you have typed up in Excel, you have a column with your expected values and a column with your observed values. Then you can use this chi-squared.test command, and you'd highlight your actual or your observed values first, put a comma, and then highlight your expected ones. And that'll also give you your p-value. And then as far as our decision, this works the same as it always does. So if p is less than alpha, we would reject the null hypothesis, which means that we have shown that our distribution is not very close to what was listed there. And if p is bigger than or equal to alpha, we do not reject, meaning we don't have evidence that it's different than the original list. So our conclusion statement here is, with a p-value of blank at the blank percent significance level, we either do or do not have sufficient evidence to conclude that our distribution, and you would talk about what those 2 distributions are, differ from the specified one. All right, so let's finish up, or actually work through this example here with these crimes. So we are testing the claim that at the 5% significance level, does the data provide evidence to conclude last year's violent crime distribution, which is represented here, is different from the year 2000. Okay, so testing the claim, last year violent crime distribution differ from 2000. Right, my null hypothesis here is that last year's distribution is going to be fairly equal to the 2000 distribution. And my alternative would be that last year's distribution is not equal to the 2000 distribution. Our assumptions and conditions. So we do in fact have a random sample here. So we can check this guy off. And then remember that these other ones are related to the expected frequencies. So we'll need to find those. So I'll do, let's see, 0.011 times my 500. So that gives me 5.5. 0.063 times the 500 gives me 31.5. And if I do that for all of these, I'll get a 143 and a 320 for the last two. So those are my expected values. All of those are greater than 1. So you can check that off. And none of them are actually less than 5. So I can check that requirement off as well. So I've met all three of those conditions. So that means what I'm going to be doing is called a chi-squared goodness of fit test. All right, to get this test statistic, I'm going to do the observed value minus the expected value, square it, and then divide by the expected. So I'm going to write this out for this first one so you can see what that math actually looks like. And then we'll take a look at how to speed that up in Excel. So for the murder category, I get 3 minus 5.5 squared divided by 5.5. For the next one, I have 37 minus 31.5 squared over 31.5 plus 154 minus 143 squared over 143 plus 306 minus 320. So this one minus this one squared divided by 320. And when I punched that into my calculator, I got approximately 3.55. All right, so let's take a look at how to get our p-value for that. And I'll also show you a way to do this calculation without writing it all out by hand. So let's switch screens here. All right, so here I have put in the 4 categories. I have my observed data and my expected data here in my spreadsheet. And so first I want to calculate this test statistic again. So I want to show you how to speed that up in Excel. So I put the formula up here. So for each category, we're going to do the observed minus the expected squared divided by the expected. So I'll put an equal sign here. I'll open my parentheses. I'll click on the observed minus, and then click on the expected. Close the parentheses and use an up caret to square it. And then we're going to divide and click on the expected one. Okay, so that gives me the part that I need for the first category. And then I can copy and paste that to the other ones. Okay, and so to get my test statistic, I just need to add up all 4 of those. And that command in Excel is equals the sum. And then I'll just highlight those 4. All right, so there's the same test statistic we got by doing it by hand. And now to get that p-value, I'll show you both of these ways. So the first one is the one that was originally listed on your paperwork. So that's equals CHISQ.dist.RT. And when I open the parentheses, it wants to know my test statistics. So I can click on that. And then my degrees of freedom. So my degrees of freedom here, I have 4 categories. So 4 minus 1 is 3 is my degrees of freedom. Okay, so I have a p-value of 0.314 or so. The other way to get that p-value is I can use equals the chi-squared, and then instead of .dist.rt, I'll do .test. And then it wants me to highlight the actual or the observed data first. So I'll highlight those 4. I'll put a comma and then I'll highlight the expected ones. So that also gives me a p-value of about 0.314. Right, so that's all the things that we need out of Excel. So we'll go back and finish our write-up here. All right, so I filled in our p-value here from our work in Excel, and that p-value is definitely bigger than alpha. So we do not reject the null. So with a p-value of 0.314 at the 5% significance level, we do not have sufficient evidence to conclude that last year's violent crime distribution differs from the 2000 violent crime distribution. All right, that is a chi-squared goodness of fit test.